We're finishing up chapter 10 now with 10.6, lattice structures in crystalline solids. Here we're going to describe the arrangement of atoms and ions in crystalline structures, compute ionic radii using unit cell dimensions, and explain the use of X-ray diffraction measurements in determining crystalline structures. So let's talk a little bit about the structures of metals. Pure metals are crystalline solids with metal atoms packed closely together in a repeating pattern. We saw that in the last section. They are malleable and ductile, so this lets them be hammered into sheets, which is malleability, and ductility means we can stretch them into wires. And this is due to the identical atoms being arranged in a regular pattern. And the different properties that all these different metals have partially depends on their size and the spatial arrangements of the atoms. So one thing we need to talk about is the unit cell of metals. So this is the simplest repeating unit of a crystalline solid. You can kind of think of it as a monomer. So for those of you that might be familiar with things like polymers or plastics, polymers are made up of a single repeating unit. Same type of thing with the unit cell. So these have lattice points that represent the locations of atoms or ions. And the cell repeats in 3 dimensions. So it doesn't just go in one direction, it goes in every single direction. So you can see the picture below showing you the black dots are lattice points, which represents where the atom or ion might be. And then you have the unit cell and showing it kind of in a bigger structure, how it's repeating in every direction. The simplest arrangement is called a simple cubic structure. And the unit cell is called the simple cubic unit cell. So this one has a layer of particles that are one layer above those in the layer below. And we'll see what this looks like on the next slide. So you have the spheres in it are not packed as closely as they could be and end up filling only about 52% of their container volume. So for that unit cell or the overall crystal. There's actually only one metal that crystallizes in a simple cubic structure, and that is polonium. That should be a lowercase o. P-O. Good old autocorrect. Okay, another term to know is the coordination number. And this is the number of particles that each particle contacts in a crystalline solid. Okay, so the coordination number of polonium is 6. The higher the coordination number, the more contacts that a particle is making in a structure. So the simple cubic structure unit cell repeats in all directions and is defined by the centers of 8 atoms. So we'll look at this. The edge length then of a cell is equal to 2 atomic radii. The unit cells only contain the parts of the atoms within them. Okay, so if you have a unit cell, you may not have an entire atom in it. So for the simple cubic structure, you have 8 atoms, but they're only at the corners in a unit cell. So you have one atom split in 8 directions. So you have 8 times 1/8 atoms. So you have 1 atom total in the simple cubic unit cell. And we'll look at this right now. So this is the simple cubic unit. And you can see, again, remember the black dots can be where some of our atoms or ions go. So you have one at each of these vertices. And you can see all this extra space, like on the faces, in the middle of the sphere, of the cube. There's lots of space. And you can see the atoms here. You know, if I were to kind of draw this a little bit better. No, it's not better. But you can see that the spheres are being divided in 8 different parts. So only an 1/8 of an atom is in each unit cell. And then another thing is that the spheres are actually contacting each other. I know it doesn't look like that looking at the unit cell, but they actually are in contact. So here is a way to be able to visualize the coordination number of 6 for the simple cubic unit cell. When we're looking at the center atom, we see it touches 1, 2, 3, 4, 5, 6. So that's why it has a coordination number of 6. Notice this isn't necessarily using the unit cell. It's just looking at the overall crystal and one atom in the crystal and how many atoms it touches. So here's a more realistic look at the simple cubic lattice. looking at the unit cell. So you can see the atoms actually touching each other as the corners in that unit cell, and you can see how there's not that many of them in the unit cell. And looking over at the lattice points, you can see the 1/8 of each atom being cut out since we pull out the unit cell. You can see we have those 8 corners. 8 corners times 1/8 of each atom gives us 1 total atom. So looking at the unit cell, the other thing you should notice is since they're touching, this is the center of the atom, and we're going to the edge, that is the radius of the atom. So the length of this unit cell for the simple cubic lattice cell is 2 times the radius, which equals the diameter of the atom. So to be able to, let's say we want to calculate the atomic radius and density for a metal. Okay, we're told the edge length of a unit cell of alpha polonium is 336 picometers. And we want to determine the radius of the atom and then the density of it. So we know polonium is the only atom that crystallizes as the simple cubic unit cell. So it looks like what you see on the right. And that the edge length of the unit cell is equal to 2r, or the diameter. So the first thing we want in A is the radius of a polonium atom. So the radius then is equal to 1/2 2r, which is our unit, which is the length of the unit cell. So we have 1/2 times 336 picometers. So then our radius, So our radius is equal to 168 picometers. So now the next part is the density of alpha polonium. And remember, density is equal to mass over volume. So we need to figure it out by figuring out we need to figure out the density of the unit cell. Because remember, density we don't care how big or how much of something we have. The density of the unit cell is equal to the density of however much polonium that we want to look at. So the first thing we should figure out is the mass of the polonium unit cell. So 1 polonium unit cell, we know there's 1 atom. Okay, we calculated that on the last slide for every unit cell. So we have 8 times 1/8 atoms. And then we know that we have 1 mole of polonium for every 6.022 times 10 to the 23rd atoms. Good old Avogadro's number coming back. And then we also know, thanks to our periodic table, that polonium has a molar mass of 208.998 grams per 1 mole of polonium. So we can see our moles polonium cancel out. And our mass of polonium, of our 1 polonium cell, is 3.47 times 10 to the negative 22 grams. Okay, so we've got our mass, and now we have to figure out our volume. So the volume of the unit cell, okay, it's a cube. So the volume is equal to the length cubed. So we have our length in picometers, and we want to put density generally in units that are easier to understand. So not grams per picometer, we want grams per cubic centimeter, or grams per cubic picometer. So we need to start by taking our picometers, and there is 1 picometer is equal to 1 times 10 to the negative 10th centimeters, thanks to my friend Google telling me this. So we have 336 picometers, and we first want to turn these into centimeters. We have 1 times 10 to the negative 10th centimeter for every 1 picometer. And then to get volume, we need to cube it. So we need to now multiply this length. So we can just write this as 336 times 10 to the negative 10th centimeters. And we are going to cube that. And that gives us 3.79 times 10 to the negative 23rd cubic centimeters. And so now our density equals mass over volume. So 3.47 times 10 to the negative 22 grams per 3.79 times 10 to the negative 23rd cubic centimeters. And we finally get 9.16 grams per cubic centimeter, which sounds like a pretty reasonable density for a metal. It's kind of hard to believe all those small numbers gives us kind of a big density, but it makes sense. All right, so I hope we're doing okay so far. I know this stuff is kind of weird. But just to kind of reassure those of you that might be a little nervous, on an exam, I would give you like the picture of the unit cell, or I would at least tell you what the length is. Like I would say, okay, this is type of unit cell, the length is this, and you would have most of your tools that you need to solve the problem. So let's talk about some other unit cells. We already talked about the simple cubic, but there's actually 4 major types of cells, and we're only focusing on the 3 cubic ones. Simple cubic, which we talked about, and then we're going to talk about body-centered cubic and face-centered cubic. So this is just kind of first giving a little introduction, showing you the different types. Simple cubic on the far left, what we've talked about. And then body-centered cubic, what that means is you have an atom at each of the lattice points, but then you also have another one in the very center. Okay? And then face-centered cubic, you have your lattice points with an atom, and then you also, though, have an atom on the actual faces of the cube. It's kind of hard to visualize, but you have 6 faces on a cube, and there's an atom there. You can see it better in the 3D version. So let's start by talking about the body-centered cubic cell. So the cubic unit cell has atoms at all corners and an atom in the center. So this forms what we call the body-centered cubic, or BCC solid. The atoms at the corner actually do not contact each other, but they do contact the center atom. Okay, so this has a total of 2 atoms. The one atom that's in the center, the entire thing is in the unit cell. And then you have, just like before with the simple cubic, the 8 times 1/8 of an atom, giving us 1 atom from the corner. So that gives us 1 and 1, gives us a total of 2. So an atom, generally we're focusing on that central atom in the body-centered cubic, touches 4 atoms in the layer above and the 4 below, and this gives us a coordination number of 8. And we also have a much higher percentage of volume in the structure being occupied, around 68%. Some examples of isomorphous metals, this means elements or compounds that have the same structure, are potassium, barium, chromium, molybdenum, tungsten, and iron. These are some examples that take on the body-centered cubic solid structure. So here's what it looks like. Atoms in the specific layer do not touch each other. So these atoms here on the corners do not touch. They do touch the one in the center, though. So you can see actually the coordination number for the center one, you can see it touching all the 8 atoms around it. So the next type is the face-centered cubic unit, or cubic solid, FCC. So this has atoms at all corners and at each center of each face. So these have actually a total of 4 atoms. So we start with our 8 times 1/8, giving us 1 atom from all the corners. And then we have 6 faces to our cubic unit cell. And it's actually about 1/3 of each atom that is on each of these faces. Oops, I'm sorry, not 1/3. That should be 1/2. Good old typo. 6 times 1/2. So that gives us 3 atoms. So it's about half the atom that's on each face of the unit cell. So that gives us 3. 3 plus 1 gives us 4 total atoms. So we do not have a whole atom in the center. There's nothing in the very center. The atoms at the corners touch atoms that are in the center of the adjacent faces along the face diagonal. So if you're looking at the face of the unit cell, you've got your 4 corners, and then you have your one here in the center. So this guy is touching these 4. Okay, and then let's see. Atoms that are on identical lattice points have identical environments. So because on each face now we have another atom here in the center, and so on. Aluminum, copper, and lead are some examples of metals that do this. The atoms are now packed as closely together as they can be, with about 74% of the volume and the structure occupied. Another name for this structure is called cubic closest packing, or CCP, and it actually has 3 repeating layers of hexagonally arranged atoms. We'll look closer at that in a little bit. But another type of closest packing is called hexagonal closest packing, or HCP. So these also have repeating layers of hexagonally arranged atoms. It is not the same as CCP. So this is not the same as the face-centered cubic unit. But each of them have 3 atoms. They have like a layer A with 3 atoms in contact with layer B above it. The HCP has a layer C that is directly above and the same as A. So it goes, A, B, A, B. Something like cadmium, cobalt, lithium, magnesium, sodium, and zinc do this. Whereas CCP has a staggered layer C. So it goes A, B, C, for instance. A, B, C. Silver, aluminum, calcium, copper, nickel, lead, and platinum are some examples. So this is looking at the face-centered cubic structure again. You can see the atoms at the corners, just like before, and then the face-centered atoms where they're cut in half in the unit cell. And so you can see there's 2 halves, 2 halves, 2 halves, giving us those 3 plus the 1 atom from the corners. So this is now looking at the CCP versus HCP structure, starting with the CCP. Again, this is the exact same as the face-centered cubic structure. So it's basically taking the face-centered cubic and rotating it. This is a better way to be able to look at HCP versus CCP. You can see layer A and then B for HCP, A, B, A, B. That's how it repeats, whereas CCP goes A, B, C, A, B, C. And you can see they're not the same. In CCP, they're staggered, all 3 of them, whereas HCP, it's 2 that are staggered. All right, so let's go ahead and look at an example. We're told calcium crystallizes in a face-centered cubic structure with an edge length of 558.8 picometers. We want to know the atomic radius and the density. So first off, we need to remember that in the face-centered cubic structure, the corner atoms do not touch each other, but they do come in contact with the center atom. So if we were to draw that, it would look like what you see here on the right. And one thing to remember is that we have 1 radius here from this corner guy, another radius from the other corner dude, and then 2 radii from the atom in the center, because the whole circle is there. So we have a total of 4R for the cross section of this face of the unit cell. So to figure out the radius, we are going to have to solve for R here. And this is a right triangle, so we are going to have to use our good old friend Pythagoras. And remember that a squared plus b squared equals c squared. And since this is a cube, a equals b. So we have a squared plus a squared, and c is equal to 4r. I don't know why this keeps doing that. 4r squared. So we have 2a squared is equal to 16r squared. We're going to solve for r here. R squared is equal to 2a squared over 16. I'm going to take the square root. So we know then that r is equal to the square root of 2a squared over 16. And just plugging and chugging, that's 2 times 558.8 picometers squared divided by 16. And so then our radius, let's go ahead and plug this in. We have 558.8 squared times 2 divided by 16. And we take our square root. And we get 197.6 picometers. So we've got now our atomic radius of calcium in the unit cell. So the next part is to calculate the density of calcium. And this is going to be very similar to what we did before with the simple cubic unit. So for starters, let's go ahead and find the mass of the calcium. So we are looking at the mass for 1 calcium, and I'm going to put UC for unit cell. And we know based off of what we talked about when we were discussing the face-centered cubic structure that there are 4 calcium atoms for every 1 calcium unit cell. And then we know that there is 1 mole of atoms, in this case calcium, per 6.022 times 10 to the 23rd atom. Let me rewrite things so I can save some room here. R equals 197.6 picometers. Okay, and then we know to go to grams to use molar mass, 40.078 grams per 1 mole of calcium. And we get that from the periodic table. We can see our units canceling to give us grams at the end. So our mass of our 1 unit cell is equal to 2.662 times 10 to the negative 22 grams. The next thing we need is the volume, and if you remember, this is equal to the length of the cell cube, since this is a nice cube, which is equal to a cubed. But we don't want to do picometers because grams per picometer is awkward, so we want to change these to centimeters cubed. So we're going to go ahead and take our 558.8 picometers and multiply them times 10 to the negative 10th is how we get centimeters. And we need to cube that. So then our volume turns out to be 1.745 times 10 to the negative 22nd cubic centimeters. So now our density is mass over volume. So 2.662 times 10 to the negative 22 grams per every 1.745 times 10 to the negative 22 cubic centimeters. And that gives us a density of 1.53 grams per cubic centimeter. Not the most dense metal, but still higher density than water. Okay, so this is just one thing that you should know when it comes to defining our unit cell. Okay, it's defined by the length of the 3 axes, so A, B, and C, so length times width times height. It may not always be a cube. We are focusing on the cube unit cell, but there are unit cells that are not perfect cubes, and they're not, so they have different angles as well. So the angles, alpha which is here, beta and gamma also define the unit cell. So it's more than just, there's more unit cells than just cubes, but we are really just focusing on the cubes. For instance, here's all the different types of lattice systems and the 14 different unit cells. Again, we really only care about cubic. Simple, face-centered, and body-centered is all we are focusing on. But there's so many other types. That's not just for another day, that's for another year and everything way down the road. So let's go ahead and talk about the structures of ionic crystals. So if you remember from before with our good old ionic compounds, the crystals have two or more different kinds of ions that normally have different sizes. So anions, they have that extra electron, tend to be bigger. Cations that have less electrons are smaller, they are more compact. So because of the size difference between the anions and cations, the structures of ionic crystals tend to be have more complex packing than metals of similar size. So the way that we get a stable ionic crystal structure is when you have ions of one charge surrounded by as many ions as possible of the opposite charge, and when you have cations and anions in contact with each other. So the way that the structure works is the anions, which are bigger than the cations, tend to be arranged in the closest packed array, and the cations themselves actually occupy one of two types of holes between the anions. So the anions are in the array and the cations are in the holes. They could be occupying tetrahedral holes, which are found between 3 anions in one plane and 1 anion in an adjacent plane, so the corners of a tetrahedron. So if you have smaller cations, this is where they will go, because these are smaller holes. Or you can have octahedral holes at the center of 6 anions, so you have 3 in one layer and 3 in the adjacent layer at the corners of an octahedron. So this is where larger cations are going to fit in. If you have a really big cation, it can also make the anions adopt a more open structure so they can fit better. So here's a nice way to be able to see the tetrahedral versus octahedral holes, showing where cations can occupy. So you can visualize it a little bit better. Here's another way to look at it. Cation size and shape of the hole occupied by the compound are directly related. So to have with the tetrahedral hole, the cation radius is about 22.5 to 41.4% of the anion radius. So it's a good bit smaller. Octahedral hole, the cation tends to be up to 41.4 to 73.2% of the anion. Then we have cubic holes, which is where it kind of just goes in the center, where the cation radius is about 73.2 to 100% of the anion radius. So technically we also have cubic holes where we kind of change the structure of the anions. So when it comes to our anion arrays, for tetrahedral holes, you have 2 tetrahedral holes per anion in the HCP and CCP anion arrays. Okay, so these still take on those HCP and CCP arrays. So because you have 2 holes per anion, that means you can have a maximum cation to anion ratio of 2 cations to 1 anion. So you can have 2 cations because you have 2 holes per 1 anion. So some examples of this are lithium oxide, lithium sulfide, and sodium sulfide. If you can also, though, have these tetrahedral holes with a ratio less than 2 to 1, so maybe you have a 1 to 1 ratio of cation to anion, what ends up happening then is you have vacant holes in your array. For the octahedral holes, the anion to hole ratio is 1 to 1, which means that your maximum cation to anion ratio is 1 to 1. So some examples of this are nickel oxide, magnesium sulfide, sodium chloride, and potassium hydride. You can have ratios less than 1. That does happen. And these would, again, have vacant holes. So this would mean that you have like sodium chloride. No, not sodium chloride, sorry. Sodium nitride, I believe, would be one. There is 1 cubic hole that can be occupied by a cation for each anion in the simple cubic array. So this was that third array that we looked at in the last slide. So that means, so for instance, in something like cesium chloride, every single hole is occupied. If you have half occupancy, you would have something like strontium hydride, uranium oxide, strontium chloride, and calcium fluoride. So you have that one hole for a cation per anion in the simple cubic array. So let's look at an example. Zinc sulfide is an important industrial source of zinc and used as a white pigment in paint. It crystallizes with zinc ions, occupying 1/2 of the tetrahedral holes. Okay, so let's look at what's important here. In a closest packed array of sulfide ions, what is the formula of zinc sulfide? So tetrahedral hole, we know that there are 2 holes per anion. Okay, and we're told that 1/2 of them are occupied. Okay, so we get that there's 1/2 of 2, meaning 1 zinc ion per sulfide ion. So we can get that the formula then is zinc, ZNS, zinc 1, sulfur 1. So here's another example. Sapphire is aluminum oxide. It crystallizes with aluminum ions in 2/3 of the octahedral holes in a closest packed array of oxide ions. What is the formula of aluminum oxide? So we know with octahedral holes, there's 1 hole per anion. And we're told that 2/3 of the holes are taken up. So that gives us 2/3 aluminum atoms per 1 oxygen. So that would mean Al 2/3 O. We can't have 2/3 of an atom in our formula, so we multiply both subscripts by 3, and so that gives us Al2O3. So let's talk about the unit cells of ionic compounds. So if you have an ionic compound that have cations and anions that are similar in size and in a 1-to-1 ratio, these will form generally cubic structures. Where the lattice point is completely arbitrary, because no matter where you choose in the structure, you will have identical structures. If you have ionic compounds that have cations and anions that are very different in size, but still in a 1-to-1 ratio, will crystallize with the FCC unit cell, with the face-centered cubic unit cell. So here's that simple cubic structure. So where you have similar size cations and anions, such as cesium chloride. So they generally do the simple cubic structure. So the unit cells, you can either say they have cations or anions at the corner. It doesn't matter, and the other one is in the center. It's all this. It would be the same ratios. Now, if you've got an ionic compound where the anions are way bigger than cations, like sodium chloride, you form the FCC structure. And these have the FCC unit cells that have the cations in the octahedral holes. Zinc sulfide, or zinc blende, another name for it, forms the face-centered cubic unit cell, where it has sulfide ions at the lattice points and zinc ions occupying half of the tetrahedral holes in the structure. So it's a cool little structure you can see here. Here's another example, calcium fluoride. This also forms a face-centered unit cell. This is a really cool looking structure. You've got the calcium ions at the lattice points and fluoride ions at the tetrahedral sites. So now we can actually calculate the ionic radii of a compound if we know the edge length of the unit cell, and you've kind of seen that already. And you've probably noticed that we had to make some big assumptions about the individual ionic shapes and contacts. For instance, we had to assume perfect spherical shapes of the ions and that they're fully contacting each other on one of the sides or on the cross section. So let's look at an example. We're told the edge length of the unit cell of lithium chloride, similar to sodium chloride and face-centered cubic, is 0.514 nanometers. Assuming the lithium ion is small enough so the chloride ions are in contact, calculate the ionic radius for the chloride ion. Note the length unit of angstrom is 10 to the negative 10th meters. Okay. So we know that this is a face cubic. So we looked at the face-centered cubic before, where the cross-section was a total of 4R. And we know that the sides of A on the unit cell are the same. So we're going to go to Pythagorean theorem again. A squared plus B squared equals C squared. In this case, it's A squared plus A squared equals 4R squared. And we are solving for R squared. 2A squared equals 16R squared. R squared equals 2A squared over 16. Square root. R is equal to the square root of 2A squared over 16, which is the square root of 2 times 0.514 nanometers squared over 16 and 0.182 nanometers, or 1.82 angstroms if you want. And this is the ionic radius for the chloride ion, because we're assuming the chloride ion, the anion, those are what's touching and what's making up our cell. And so that's the radius of the chloride ion. So now, where we get some of this data is through the process of X-ray crystallography. And this is used to determine the size of the unit cell and arrangement of the ions. The way it works is you send X-rays to the crystal, which diffracts them. They undergo diffraction, meaning that that the direction that those electromagnetic waves are traveling changes. And you can record the angle that it bounces off. Okay, so we use what's called the Bragg equation to relate the wavelength of the X-ray is lambda, the integer factor n, and angle of the diffractive beam theta for constructive interference. So we always have destructive and or constructive interference. So if you remember, destructive interference is where the waves, the peaks of one wave line up with the valleys of the other and they cancel out. Constructive interference is when the both peaks and both valleys of the two waves are lining up. Okay, so this is just a nice visualization. I can't speak today. So here's also a nice way to be able to see the diffraction of the X-rays. So you have some distance traveled by two waves. So you send these two waves at your particle, and they are scattered by your crystal at these angles, and they can either line up or go through constructive interference or destructive, depending how they line up. So we use what's called a diffractometer. So it's going to go ahead and send the beam of X-rays to the crystalline material, and then and then the image surface shows the diffracted X-rays, giving a diffraction pattern that we can analyze to figure out structure. So for an example, if we have some X-rays with a wavelength of 0.1315 nanometer used to produce a diffraction pattern for copper, we're told the first order diffraction, so n equals 1, occurred at an angle theta of 25.25 degrees, and we want to know the spacing between the diffracting planes in the copper. So the Bragg equation is n lambda is equal to 2d sine theta. We're solving for d here, so we know that d is equal then to n lambda over 2 sine theta. So now we can go ahead and plug and chug. Notice it really doesn't matter. The distance is going to be the same units as the wavelength. So unless you're told to put your wavelength in a specific unit, it doesn't matter. You can leave it as is. So n is 1 times lambda 0.1315 nanometers divided by 2 times the sine of 25.25 degrees. So this calculates out to be a distance of 0.154 nanometers. So the distance between the planes is 0.154 nanometers. So where X-ray crystallography, I mean, it's a major thing in science. One of the biggest parts of it is thanks to Rosalind Franklin, who helped whose work helped Crick and Watson figure out the structure of DNA. So her research looked at X-ray diffraction. She actually started looking at coals, the structure of coal, which helped in the British war effort in the early 50s. And then her and her student tried doing X-ray crystallography on DNA, and noticed that it had two forms: a long, thin fiber that formed when it was wet, and a short, wide fiber when dry. And this information, these images, helped Watson and Crick determine that DNA forms a double helix and figure out details of its size and structure. Just to kind of a little bit more information on Rosalind Franklin, she also looked at viruses and RNA, and really radically changed the body of just knowledge in virology and chemistry and biology. She actually passed to ovarian cancer at the age of 37, but up until her death, she worked and researched. So, really awesome person. The University, or the Chicago Medical School of Finch University of Health Sciences actually changed its name to the Rosalind Franklin University of Medicine and Science in 2004 in her honor. And they adopted an image of her X-ray diffraction image of DNA as their official university logo. So, pretty cool stuff. That does it for chapter 10. I know the last half of it kind of goes a little nuts from the first half. Please know on your final, I'm not going to go super in depth with the questions. If anything, they'd be more similar to the examples here. As usual, guys, if you have any questions, please let me know. I'm here when you need me.